Good evening, learners, and welcome, Rahul sir, once again for the session. And now you can start the session, sir.
Yes, thank you so much, sir. Good evening, everyone. Okay, so I guess we have seen some topics related to the queue in our previous session, right? So let me briefly revise all that stuff. So I guess we have seen the definition of a queue. Then we started with the definition of a queue. Then we have seen how one can represent the queue as an ADD. Then we try to relate that concept with our real life examples. Then then after we have seen the linear implementation, that is with the help of array and with the help of linked list, right? And we try to understand the basic operations like whether when the queue will be empty, when it will be full, then how to insert the element, that is nothing but our enqueue operation, how to remove the element from the queue, that is dequeue operation, and how to check the frontmost element from the queue, that is nothing but the peek operation. Thereafter, we have seen some codes related to the queue with the help of C programming language. And I guess we have moved towards the types of queue. And within that, we have seen the circular queue, right? Because our linear queue, we're having the drawbacks. Like if once the queue is full and if initial some places are vacant after performing the dequeue operation, still we can get the error like the queue is full because our rear has reached the end of the queue, right? Therefore, we try to modify our logic and try to make it as a circular one. So for that, we have just used we have just taken the help of modulus operator, right? So the modulus operator that we have seen, and we try to implement the circular queue. That I guess that was our last point in our previous session. Now today we will try to understand the next kind of queue, that is, or next type of queue, that is nothing but our priority queue. Yes. So queue data structure is having many applications, and one of the application that we can find for the queue is among the different system softwares, which includes operating system, compilers, and then our some device drivers, etc. Right? So this priority queue is actually a special kind of queue in which every element will be associated with some priority value, right? And most of the time we see that the as some certain integer value or any kind of information is associated with every element within the queue. And if we deal with the integer values, then one can say the lower priority value will carries the higher priority. It means if certain element is assigned with some priority value, let's say it is 0, then one can say the particular element will be having higher priority among the other elements within that queue or within that particular set, right? So here the basic terminology or basic idea is the elements will be served based on their priority, not by using the logic of first in, first out, right? As we are going to assign some priority value to each one of them. So they will be served, they will be processed according to the priority value. Then here, the higher priority elements must be served very first, or they will be treated, or you can say they will be prioritized, right? So if the elements, if there is a tie in between the two elements, or you can say if there are two elements which are having same priority value, right? Now, in order to break that tie, we have to again shift back, or we have to again use the logic of our linear queue, that is FIFO queue. First in, first out order, they will be served, or you can say they will be processed. Now here again, this priority queue will be have two types, like ascending priority queue and descending priority queue, right? So depends upon the values, the elements can be inserted arbitrarily, but the smallest value or the smallest element, if it is removed first, then such a kind of queue is called as ascending priority queue. Like the smallest element is coming out first. So at the end, you can see the last element will be the largest element among all the remaining elements within that queue, isn't it? So that's why it is called as ascending priority queue, or you can say the elements are removed from the queue in ascending order, right? So there is no order, or you can say there is no particular way of enqueuing the element within the queue, but we are restricting ourselves, or we are restricting this type of queue for deletion operation or for dequeue operation. The elements will be removed from the queue in a such order that they will be having a sorted way, like ascending order, right? Now in a descending order priority queue, right? So it is just opposite of our ascending order priority queue or ascending priority queue. So this allows the deletion of only the largest element first. So in this case, if we go and remove all the elements, so the last element will be removed from the descending priority queue will be the smallest one among the remaining, isn't it? So then there is again one way of implementing, or one type of priority queue is minimum priority queue, right? So here, if we are not ordering them, if we are not having certain order of their removal or certain order of their insertion, then in that case, we obviously need to assign some value with each and every element, priority value in this case, right? So now, depending upon that priority value, we are having two types. One is minimum priority queue and second is maximum priority queue. Now in a minimum priority queue, the minimum number of a value gets the higher priority. Like I just said, if certain number, if certain key, or you can say certain information within the queue is assigned with some minimum value, let's say 0. So that value is having highest priority. Okay, that value is having highest priority, and opposite way, one can say the lowest number of the element gets the or you can say the lowest number of the element gets the higher priority. Okay. Now in a max priority queue or maximum priority queue, the max priority queue is just opposite of your minimum priority queue, where the maximum number value gets the higher priority. Okay. So mainly, if we see in a CPU scheduling or in any operating system algorithms, the minimum priority queue is utilized, right? So the processes where the whose value is lower, those processes will be executed first, right? So these are the different types of priority queue. Now, next point comes in our mind is how to implement them. We have just seen two different types of priority queues depending upon two different strategies. One of the strategies that the order of insertion or removal will categorize the queue, or some particular value assigned with any element within the queue is going to categorize it, right? So how we can implement it? So there are two different ways of implementing the priority queue is one of them is using the ordered array. In an ordered array, the insertion or enqueue operation is going to take big of n time, because it enters the element in a sorted order into the queue. As all the elements are sorted order, so obviously the first element, let's say if they are in a ascending ordered form, So the first element obviously will be having minimum value, and element will carry the maximum value within that set or within that group of elements of our queue, right? Therefore, if we have to insert them, then or we have to perform the insertion operation, then obviously it is going to take big O of n time, because we need to iterate up to n elements and we need to reach to the particular position where we can insert the new element. But in a deletion case or in a DQ case, it takes only big O of one time. Why? Because the elements are already in a sorted order, right? So if they are in sorted order, if it is ascending priority queue, so the minimum element will be the first. If it is a descending priority queue, then one can say the maximum element will be the first. Okay, so we just need to remove the first element, that is from the front, right? So it is always going to take the constant time. So our deletion operation will require only big O of one time complexity, which represents the constant time. I hope you people remember the time complexity. Yes? And these are the asymptotic notations that we have used while representing the complexity for the algorithm as well as for the program. Right? So can anyone tell me what big O represents? Which case big O represents? Yes? Whether it represents the best case, worst case, or average case. That is my question. Because like you people just have seen, if in order to implement the queue data structure, there are multiple ways, right? We have seen the linear queue, which we have implemented using array as well as using linked list, right? Then furthermore, we have moved towards the circular queue. Again, it can be implemented using array as well as using linked list, right? Now we are looking after the next type of queue. So it is again a queue, but having some different properties, having some different characteristics. So if we are organizing that same kind of data in a different ways, so obviously we need to analyze it. Which way of organizing the data is perfect for us, depending upon our application and depending upon our use. Yes. So therefore, in order to analyze such a things, yes, someone says base case. Okay. See, we always compare or we always analyze our programs or our algorithms for worst case analysis. Okay. So big O always represents the worst case scenario, right? Because in a worst case, what will happen with our program or with our algorithm, that we need to check. That's why we always talk about the big O, not with theta and omega notations, because they represents the average and the best case complexity. So we cannot execute the algorithms or we cannot execute the programs in a ideal situations, right? So that's why we have to prepare or we have to analyze our data organization. That is nothing but the data structure for the worst cases most of the time. That's why I have utilized the worst case scenario over here, right? Okay. Now the next one is, if you don't have ordered array or the data insertion or the data is not inserted in a particular order, right? Either ascending or descending, then we can have the unordered array, like our usual array, regular array one can say, right? So in unordered array, so deletion is going to take the big of n time complexity. Why? Because you have to select a particular element among the remaining n minus 1 in order to delete it, right? So obviously we need to go and search them. We need to find out the particular element to be get deleted from the queue. So it is going to take n iterations, or you can say it consumes big of n time complexity. Yes, but for the deletion, sorry, for the n queuing, or you can say for the insertion, so they can be inserted arbitrarily, right? So it will always take the big of one time complexity, because if you are using the FIFO logic, then the element will be inserted from the rear end. So we just need to insert it at the end, or you can say you are going to append the data at the end of the queue every time. But if you are prioritizing the information that you have just appended, so we need to remove it depending upon the priority. Now for that case, if your array is unordered one, then we have to search for the element to be get removed from the array, right? So that searching will require big of n time complexity. Okay, I hope you people are getting it. Yes. Now let's move towards the next kind of queue. Right now, till now we have seen the linear queue, then we have seen the circular queue, and we have also seen the priority queue. So priority queue is also a linear queue, but every element will be associated with some priority value, right? And everywhere we have seen there are only two ends. One end for insertion, we called it as a rear end, and one end for removal, we called it as a front end. Now, if my queue is having, or I can insert from both the ends, and as well as I can remove the element from both the ends, then such a kind of queue is called as double-ended queue. Obviously, it will be tricky one. It will be difficult to implement, right? Because here we need to keep the track from which end we are going to insert the value, as well as from which end we are going to remove the value, because both the ends are now capable for insertion as well as for the deletion. But in our previous case, the rear end was the only end through which we were inserting, and front end was the end through which we were removing the element. Yes. So here the extra overhead will be there, right? We need to keep the track from which end we are inserting, and simultaneously we again need to look after from which end we are supposed to remove the element. Yes. Yes. So here the end at which the insertion occurs is also known as the rear end, whereas the end through which the deletion occur is we are going to refer it as a front end, right? So it is like a linear queue, but insertion and deletion operations are going to perform from the both the ends, right? Or one can say this is the generalized version of a queue, right? So there is no restriction. You can go and append elements at any particular end, or you can go and remove the element from any particular end, either front or rear, right? So if such a kind of way, or if we have organized our information in this way, then that queue can be referred as a D queue, that is double-ended queue. Okay. So this queue can be used both as a stack and queue, right? Like a stack, it is going to allow us to insert the element from the one end and remove the element from the same end, right? We have seen that with the in the context of stack, that we are inserting the element from the top as well as we are removing the element from the top, right? So it is facilitating both the ways, or you can say both the data structures, double-ended queue. Okay. So if the insertion and deletion operations are performed from the one side, then we can treat it as a stack. That is, it is following the last in, first out manner. You can see with this particular diagram, right? And if we are using one end for the insertion and another end for the removal, then it is acting like a first in, first out queue, linear queue. Okay. So again, there are two types of queues. One is input restricted queue and another one is output restricted queue, right? So I hope you people are getting the idea by looking at these particular names, right? If it is input restricted queue, then it means there are some restrictions which are applied for the insertion. Okay, like you can see in this particular diagram, this is the only end through which we can insert the element, but both the ends can be used for removal of the element. Okay. So in an input restricted queue, the insertion is applied at one end, while the deletion can be done from both the ends. You can remove the elements from any one of the particular end, right? You can do this from both the ends. Now, output restricted queue. Yes, you can see we can insert the element from both the ends now, but there is a restriction over the dequeue operation, right? You can remove it from one of the either end, either from the front or from the rear. Yes. So in the output restricted queue, the deletion can be applied only from one end. So for this particular example, you can see the rear end is only used for removal of the element. But from the front, you can insert the element, and from the rear as well, you can insert the element. Okay. So while implementing it, it will be again very difficult, isn't it? Because we need to keep the track of all the both the two ends, and we need to keep the track which end we are using for insertion, or depending upon the type, whether it is an input restricted queue or whether it is a output restricted queue. Yes. So that's all about the different types of queue. So linear queue, first we have seen, then circular, then priority queue, and now we have just seen the double-ended queue. Okay, double-ended queue. Now we are moving forward towards the applications of the queue. So queue can be used in the CPU scheduling, or you can say in a process scheduling in operating system. Okay, so it helps us to manage the task. It helps us to manage the different processes which are running concurrently, parallelly within the operating system, right? And as there are very limited resources available to the system, so it helps us to manage them and use them very efficiently, right? So the process scheduling, where we can categorize our queue into different categories like ready queue and job queue. So the queue which holds all the processes which are ready for the execution or which are waiting for their turn to grab the chance of execution over the CPU. Such a kind of processes are called as ready queue. So if we bundle them together, arrange them in a queue, then we will form the ready queue, right? And there is another queue, device queue, or you can say, if there is a particular device, let's say there is a device called as printer, right? So if I have opened 4 different files and one after the another, I have given a print command. So is it going to happen that all my 4 files will be printed at a time? No, because printer is having limitation. It is a hardware device, right? It is having a limitation. It can print a page at a time from one of the source. Or you can say it is going to print it from, it is going to print it line by line from top to bottom and from left to right, isn't it? So if you have opened 4 different files and if you give the print command, so obviously we need to maintain a queue for that, right? Now for on our behalf, the operating system maintains the queue for that particular device, right? Now once my first file is get printed, now the chance will be given to the second file, right? Then after third file and then fourth file. So we can see the order by which they have entered the queue, the same way they will be processed or they will be served. So it is following the queues logic. Okay. And there is one more algorithm in a CPU scheduling known as round robin algorithm, where we are not allowing every process to be execute for its burst time, entire burst time. Okay. So we are distributing them with depending upon certain time quantum. We are allowing them to be get executed for a certain amount of time only, and that time is nothing but the time quantum. Okay. Now suppose there are 5 different processes. First process, suppose we are giving 2 units of time. Then once 2 units of time is over, then the chance is given to the second, then third, then fourth, and up to fifth. Now once we reach to the fifth process, and if some of the portion of my first process is still remaining. Now we are giving a chance back to the first process, right? So we can see that we are moving in a circular way. Now here you can find out the applicability of your circular queue. Okay, so you have got let's say 5 different processes. You are processing them with the help of time quantum, that is by the principle of round robin scheduling. Yes, so they are executing one after the another. Once we reach to the last process, we are again going back to the first process so that there will be a fair chance given to the each and every process, right? So our response time will be better in that case. Yes. Now, in a resource allocation, like system is always having a limited resources like our CPU, memory, printers, or any hardware device, you can say, they are always in a limited way. So if there are n number of programs or processes executing, so they need to wait, right? They need to wait for their chance or their turn, because number of resources are not infinite, they are limited always. Okay, so just we have given the example of printer, that is printer queue disk scheduling, right? So if your hard disk or your disk is made up with multiple, you can say multiple disks, right? So, and if there is a request for accessing a particular file from the disk, or you can say particular location from the disk, right? So if you are making multiple requests, so they will be queued one after the another, and the way they have entered the queue, they will be processed. Okay, you can find out the applicability of the queue in a networking as well, right? So the through the network, the data is going to be get transferred, right? And network is made up with the multiple devices like routers, switches, hubs, etc. Right? So the order by which the elements or the devices are chosen for transferring the data from one end to another end. So that order will be followed, and the data will be transferred from source to destination, right? So that's it from this particular unit queue. Now, if you have any doubt, you can ask, or you can ask the questions at the end, because I wish to start with the next topic, that is queue. Sorry, that is tree. Okay. So till now, we have seen all the linear data structures. We actually started from array. Yes. Then we have seen the stack. Then we have seen before that I guess we have seen the linked list, then stack and queue. Okay. So all those were our linear data structures where the data was organized in a particular order, right? Or you can say from one point, there will be only another point accessibility available in those data structures. Now today, or within this particular lecture, we are going to explore the next data structure, which is very important and which is helpful when we are organizing the data in a hierarchical form or in a hierarchy, right? And that data structure is nothing but the tree. Okay. So first of all, the tree is the hierarchical data structures which consist of nodes, and those nodes are connected by the means of edges. Programmatically, we are going to connect them by the means of pointers. Okay. So basically it is a non-linear data structure, which is nothing but the collection of elements known as nodes. They are connected via edges, and they are connected in such a way that there exists a path between one node to another node. Okay. So if anyone knows the concept of a graph, so tree is nothing but the acyclic graph. It means if you follow particular path, then that path is not going to form a loop within the tree data structure. Okay, this is actually one of the characteristic, or you can say the property of a tree. So it is a acyclic graph. It means there are no cycles within the tree. Okay, theoretically, one can define the tree. It is a data structure where there is a specially designated node known as root, which is nothing but the starting point of tree, or this is a place from where we are going to organize our information, or we are going to arrange the data within it. Okay. So in a tree, there will be always a specially designated node known as root. And the remaining information, or you can say remaining nodes, are partitioned into n disjoint sets where n must be greater than or equal to 0. Okay, it means what? If you are having certain number of elements or certain number of data to be get stored, then there must be one starting point. We will name it as a root, right? And the remaining elements will be partitioned into multiple disjoint sets. And that multiple disjoint sets can be either 0 or it can be n. Okay, it can be n. So let's say there are n disjoint sets like T1, T2 up to Tn, where every disjoint set is representing a tree itself. Now, I hope you people are getting this particular definition. Now, from this definition, can anyone recall any kind of concept of a programming? What kind of principle is utilized while defining the tree data structure? So if here, let me explain it again. See, we are having some finite number of information, let's say. Okay. So the concept says we have to distribute this, or we have to organize this finite number of data, let's say n. Okay. You can do this organization like there will be some starting point. Okay. There will be some of like if you are having a class, so I am naming n, there are n number of students in your class, right? And I am naming one of you is the, yes, one of you is a monitor of the class. Let's say it is the root. It is the starting point from which I can get access of remaining student from this particular class. Okay. So the monitor is there. Now the remaining, let's say n minus 1 students are remaining now. Yes. Now we have to divide them into different disjoint sets. Okay. Now those sets can be either it may be 0, yes, or I can say the remaining elements are not there. Only one student is there in a class. Okay. So monitor will be the only one student remain in the class. That can be another situation. Let's say now there are 3 students in a class. Okay. So monitor is there, and along with that there are 2 students. Right. Now let's say there are 20 students. Another case. So monitor is there and remaining 19 students. Now I can divide them like there is a set of 9 students and remaining will be the set of 10 students. Yes. Now the set of 9 and set of 10 students, they can be a same kind of, they are following this same kind of structure. Like suppose those 10, one of them is the monitor, and again they are further dividing the remaining 9. Yes. So here what we are doing, we try to form a law, or you can say a rule, right? And we are imposing the same rule towards to the next disjoint set or the next remaining elements within my set, or you can say within my collection. Okay. So it tells us that there obviously someone says there is a parent-child relationship. Yeah, we are going to explore that in our upcoming slides. But this definition tells us that if there is from n elements, if one of them is a root, right, and remaining are divided into some disjoint sets T1, T2 up to Tn. Okay. Now those T1, T2, Tn are also following the same rule. They are a tree themselves. Okay. So here it says us, or it tells us that we are working like a recursion. Like we have seen the example, if you recall, we have seen the example of factorial of a number. Suppose I wish to calculate the factorial of 5. So what I did? Yes. The recursive statement was in that case n into factorial of n minus 1. Yes. So I have taken n aside and I am applying the same logic on remaining n minus 1. Okay. So what that n minus 1 is doing now? N minus 1 will do n minus 1 into factorial of n minus 2 and so on. Up to 0 we will reach. That was our logic if you recall. Okay. We have seen that in the case of stack, I guess. Okay. So this tree definition is itself pointing towards the recursion. Therefore, while implementing the tree, we are going to use the recursion. Right? If you are using recursion for implementation of a tree, then it will be easy, or you can say the implementation will be efficient or easy for us. Okay, and that those disjoint sets T1, T2, Tn will be our subtrees of that given root. Okay, I hope you are getting the definition of a tree. Tree is nothing but a nonlinear data structure, first of all, right? It is used to represent the hierarchy. Like we do have a hierarchy at our offices, in our colleges, or any government, non-government, non-government, or any another organization, right? Like there is a CEO, then under the CEO, there are some, let's say, some directors, under those, there are some managers, under those, there are some leaders, right? TLs are there, and under those, there are some different people are working. Like developers are there, testers are there, designers are there, and so on, right? So in order to represent such a kind of hierarchy, we can organize that kind of information with the help of tree and very efficiently. Okay, this is very one of the widely used data structure and very efficient one. We will see that. Okay, so the characteristics tells us there will be one specially designated node root, right? Now each node can have either 0 or more childrens. Okay, so mathematically, the empty set also can represent the tree, because the definition says there are 0 elements. There can be a 0 elements within the tree. Okay, mathematically it is true, but while organizing the data, if there is no data, then how we can organize, isn't it? There should be at least one data, right? So for our in our case, we are not going to consider tree is not having anything, or the tree elements are empty. Yes, because there should be something, then and then we can organize it. Otherwise, we cannot do anything. Okay, and most importantly, tree is a cyclic graph or a cyclic structure, where if you follow a particular path, then you cannot come back to the same path, or you can say same position or same node. Okay. Now let's move towards some terminologies. Let us try to explore some terminologies within the tree. So the first thing that is node. So node is a basic unit of storage, or you can say a node is a place where we are going to store or keep our data. Okay. Now here in a diagram in the right, you can see there are certain nodes. Okay. And there is a specially designated node also. Let's say this A is a specially designated node root, right? Now the remaining data is now partitioned. Now for the A, the data is partitioned into two sets. Let me annotate. Okay, for A, the data is partitioned into two sets. Okay, there are some information in the left and there is some information in the right. Now further, those two sets are following the same rule. There is some specially designated node in the left side and there is some specially designated node in the right side. Okay, you can say these are the subtrees of A. Let's call it as a left subtree and this is our right subtree. Okay, and they are connected. They are connected by the means of edges. Okay, so the edges are used to represent the connection between the nodes. Right? Now you can see further if you explore the left subtree. Now you can see the left subtree is now having three different subset like this. Okay, this is left subset, this is right subset, and this is middle subset. Right? And they are also following the same rule. Okay, so this is how we can relate this with the help of, or we can relate this with the recursion. Okay. Now, in a tree, if there is a node which does not have any further nodes, or you can say a node which does not have any children, then such a node is called leaf node. Now, in our given case, or in this example, G and H are the leaves of my tree, or you can say the leaf node of my tree. Right? Now, again, there is a parent-children relationship. So the parent node is the immediate predecessor of a node. Let's say, let's talk about the node E, right? So the immediate predecessor of the E is B. So you can say B is the parent of E. B is a parent of E. Now, B's parent is A. Or you can say A is having two children, B and C. Okay. So the child node is nothing but the successor of that particular node for any particular given node. Okay. So the leaves does not have any childrens. Okay. Now the siblings are nothing but the nodes with the same parent. Now here you can say D, E and F are the siblings because they are having same parent, that is B. Okay. But F is not a sibling of G because their parents are different. Their parents are different. Okay. F and G are not siblings because their parents are different. Okay. Now, furthermore, there are more terminologies. So next is a path. Path is nothing but the number of successive edges from source node to the destination node. Now here, suppose I wish to find out the path between A and H, right? So if you follow this particular path, then we can see that we have encountered with the two different nodes. So from A to B, I need to traverse. Then from B to E, I need to traverse. And then from E, I can reach to H. Yes. So this is going to form a path from A to H, or you can say from H to A. Okay. Now, next concept or the next terminology, which is very important, is nothing but the height. Okay. So a height is nothing but the number of nodes represents the number of edges on the longest path between that node to the leaf node. Right? So here you can see in height context, you can see A is at a height 3. Why A is at a height 3? Because there are 3 different edges. Right? We have to traverse or we can go to that particular longest path. Yes. Now, B and C are at the height 2. Yes, not B actually. Only C is at the height 2. B is at the height 1. Because there is only one edge between B to its leaf node. From B to its any one of the leaf node. Okay. So from C, there are 2 different edges so that we can reach to the leaf node. So height of a node represents the number of edges on the longest path between that node to the leaf node. Right? Now, the maximum height of any particular node within the tree is nothing but height of a tree. Okay? So height of a tree, obviously, which node will be having the highest height? So by looking at this particular example, one can say the root is having the highest height. Okay. Now next is depth of a node. Depth of a node represents the number of edges from the tree's root node to a given particular node. Okay. Now the distance of a node from the root is always treated as the depth at the depth 0. Now you can say B is at the depth 1 from the root. E is at the depth 2 from the root, that is A. Okay. So it shows how many number of edges are there from a particular given node towards its root. Okay. Now next is degree of a node. Degree of a node represents the number of children of that particular node. Now here you can see C is having only one children. So the degree of C is 1. G does not have any children. So the degree of G is 0. Right? A is having two children, B and C. So the degree of A is 2. B is having three different children, D, E, and F. So the degree of B is 3. Okay. Now, once you know what is the degree of a node, then we can easily find out what is the degree of a tree. Okay. So maximum degree of any node in the tree is called as degree of a tree. Yes, degree of a tree. So for this first diagram, can anyone tell me what is the degree of this tree? I just want to know the degree of a tree, not the degree of any particular node. So degree of a tree is nothing but the maximum degree of a node in the tree. Yes, very good. I got one response. Yes, the maximum degree of a node is 3. Yes. So the degree of my tree is 3. Okay. So the degree of this particular tree is 3 now. Okay. Now moving forward. Here we have till now we have just seen all the generalized concept or generalized terminologies. Okay. In the context of a tree. Okay. Now as we have to implement it practically. Now we have to explore some one can say the practical examples. That is how one can organize the data, right? Now here, if your node does not have any restriction over the number of childrens, then it is very hard to implement it. Either mathematically, represent it mathematically and implement it practically. Because here we always go and reach to every particular node and we need to take the decision whether or where we can keep the data. Okay, let me give you one simple example. Suppose this is your data. This data we have to organize. And there is no restrictions over the number of nodes can be attached to any particular node. Okay, suppose the data is coming in alphabetical order. Let's say you can see A, B, C, D, E, F, G, H. These many characters or these many data that we have to organize. Okay. So one of the ways, as per the trees rule, there must be some specially designated node. Let's say A comes first. So I have organized it into the root. Let's say it is a root. I am representing it with R. Right? Now when B comes, so I need to take the decision where to put this B. Right? And we are not restricting any node to be get attached to any another node. Right? Like here you can see there is no particular restriction. A is having 2 children, B is having 3 children, E is having 1 children. So there is no particular restriction. Right? But if you go and have some another side of this particular data organization. So I can attach B to this A, right? I can attach C again to this A, and I can attach D, okay, like this, because as per the definition that we have just seen, our remaining data or remaining information need to be distributed into n disjoint sets, right? So suppose 1, 2, 3 and 5, 8. 8 information is there, like from A to H. Yes, A to H. There are 8 different information or 8 different data that we wish to organize, right? So I can organize them like this also. Okay, I can organize it like this also. Like A is there, so let's call it as a root. Next comes, attach it to A. Then when C comes, attach it to A again. When D comes, again attach it to A, right? Then when E comes, again attach it to the root node. So everyone is attached to the root. Yes. So you can see that there are many edges coming out of the root. Okay. But still, this organization follows the definition of a tree, isn't it? Because everywhere there can be n disjoint sets where n is greater than or equal to 0, isn't it? So B is having subsets, or you can say B is having subtrees which are equal to 0. Therefore, this also follows the definition of a tree data structure. But obviously, if I wish to implement it practically, then what I need to do? I need to declare a structure with n number of pointers. Yes, where that structure will be able to hold some data, let's say character data, and there will be n number of pointers. Now, what will be the size value of n? We can't say, right? If after h there will be one more element, right? Let's say I comes. So again, we will allow I to get added over here. Yes, therefore, there will be no restrictions theoretically. But obviously, practically, we need to restrict ourselves that how many nodes can be attached to any another node. Okay. So let's come back to the point and let's try to understand the practically possible, practically implementable version of a tree is nothing but the binary tree. Right? Because it was n-ary tree. You can see in this example, this is n-ary tree. Here, a tree can have 3 childrens. Right? Sorry, a node in a tree can have 3 childrens. Now, furthermore, a node can have four childrens or 5 childrens or n number of childrens. Isn't it? But we need to restrict ourselves because we need to implement it. Okay? We need to implement it. And for the implementation purpose, the practically implementable, or you can say implementable version of the tree is nothing but binary tree. Okay? Now, as the name suggests, binary, it means what? A node can have at most 2 children. Every node will have at most 2 children. When we say at most 2 children means there may be 0 children, there can be 1 children, but there will be at most 2 children only. Okay. So binary tree is a finite set of nodes that is either empty or consist of the or consist of a root and 2 disjoints binary trees called as left subtree and right subtree. Okay. So here the data will be divided into 2 sets at every level within the tree. Okay. And that 2 subsets will be nothing but our left subtree and right subtree. Okay. So here we are restricting ourselves that every node will have at most 2 children. So while declaring the structure or while implementing it, we just need to declare 2 pointers. One pointer point to the left subtree and another pointer, let it point to the right subtree. Okay. Let it point to the right subtree. Okay. So it has a unique path. So obviously, if we restrict ourselves, so there will be a unique path from the root to every other node, right? Like this, just shown on your screen, that this tree we have restricted to be a binary tree where every node we can have at most two children. Okay. So there will be a single path from root to any particular node. Otherwise, if there are, if it is the multi-way tree, or you can say n-ary tree, then there can be a multiple paths for reaching from one node to another particular node, right? Okay. So first, let's try to understand different types of tree. So the first type of tree is called as full binary tree. That full binary tree is nothing but which follows this principle that each node of a binary tree has either two children or no children at all. So we are again refining it, or we are making our rule more stronger. If you have a children, then there should be two children or there will be no children at all. Okay. So every node in a tree is either 0 or two children. If such a kind of tree is there, then such a tree is called as full binary tree or strictly binary tree. Now, where to use such a kind of tree? These are used for representing the mathematical expressions. We will see the expression tree at the end of this particular chapter. Okay. So, I hope you are getting the strictly binary tree. So rule is very strict. You either have a children 0 or there can be two children. There is no concept of having one children. Okay. So if you have a children, so it will be 2, otherwise no children. Then such a kind of tree is called as strictly binary tree or full binary tree. Now next is perfect binary tree or complete binary tree. Right. So if all the levels of the tree are completely filled except the last level, and the last level has all the keys as left as possible, is said to be a complete binary tree, is known as the complete binary tree. Okay. So the complete binary tree is a tree whose all the levels are filled from top to bottom. See, this is the hierarchical data structure. So root is at the top, right? And all the leaves are kept at the bottom. So we are moving from top to bottom. Yes. So the root is always kept at the 0th level. So we go and fill those levels one after the another by the data. Okay. And if they are filled, then in such a way that all the levels are full, then such a kind of tree is called as complete binary tree. Okay. Then there is another type of tree that is almost complete. Okay. It is almost complete. It means all the levels are filled except last one. Yes, except last one. And if the last level is not completely filled, so it should be filled from left to right only. Okay. It should be, or it must have filled from left to right only. Then another last type of queue is called as queued binary tree. Okay. So here the number of left or right childrens are going to dominate the type. Okay. So if every node is having only left children, then such a kind of tree is called as left skewed tree. And if every node is having only right children, then such a kind of tree is called as right skewed tree. Okay. So skewed tree is nothing but a tree in which there are either one children. Either it will be a left side children or it will be a right side children, but not both. Let's try to understand them with the help of diagrams. So the first diagram is nothing but the full binary tree. Okay. So there is a rule like if you have children, then there must be 2 children. Yes. So suppose there is no E, then this is not a full binary tree, right? Either B has a children, B has a 2 children, or there will be no children. That rule we need to follow. Therefore, it is strictly binary tree or full binary tree. Now, next is complete binary tree. In a complete binary tree, what happens? So, the levels are filled from top to bottom. Okay. So, the root is kept at the 0th level, right? And all the leaves are at the bottom. Okay. So, the children's or the subtrees of a root at the level 1, and the subtrees of a root are at the level 2, and so on. Okay. So this is the complete binary tree, which shows that, but in this kind of tree, if let's say this node is missing, this node is not there, but still you can say it is a complete binary tree, because it is not necessary to follow whether it is a strictly binary tree or full binary tree. Okay. So the levels must be filled from top to bottom. Okay. From 0th level to the maximum level. Then and then this is called as complete binary tree. Now what is almost complete binary tree? So if how many levels are there? This is my 0th level, right? This is first, this is again second, and this is third level, right? So a tree is called as almost complete binary tree if there are n levels, then n minus level must be filled completely. So it is complete till level 2. You can see within this box, it is complete to up to the level 2. But last level is incomplete. Last level is incomplete. Okay. Therefore, it is called as almost complete binary tree. Right. But while filling the information, suppose there is one more node. Let's say this is a node. Right. And let me put some value 10. So this is not the complete binary tree. Sorry, this is not almost complete binary tree, because the rule says data will be filled from top to bottom, level by level, and from left to right only. You can see those arrows. Okay. Data must be filled from left to right only. So this is not a complete binary tree. If almost complete binary tree, if I inserted 10 over here, yes, if I have inserted 10 over here, then it is not the almost complete binary tree. Okay. So next is skewed binary tree. Okay. Now you can see over here, every node is having only left children, right? And here, every node is having right children. Therefore, this tree is nothing but our left skew tree, and this is our right skew tree. Okay. So these are the different types of and very important types of queues that we are going to utilize. Okay. Now, how one can represent it? Like other data structure, every linear data structure that we have implemented till now, we have seen their representation. We have represented stack using array as well as using linked list, right? We have represented queue using array as well as using linked list. Now we have to represent this hierarchical information. This hierarchical information or data with the help of array as well as using linked list. Okay. So first thing is, let us try to understand how one can represent a tree data structure with the help of array. Okay. So if we represent tree data structure with the help of array, it is called a sequential representation, and the data will be stored within an array level by level and starting from the 0th level. So who is at the 0th level? Root is at the 0th level, right? So if we represent it with the help of array, so root will be kept at the 0th index of that array. right? And further, we can go and store, further we can go and store the childrens of every successive element in the every successive level of that particular tree. Okay. So here, what we can do, we just need to number the elements from level by level and from left to right. That is, zeroth level numbers will be zeroth level elements will be numbered first, then first level, then second level, and third level, and then all will be numbered from left to right only. Okay. So if you do so, then we will realize that we will require the array. We will require the array which is of size 2 raised to h plus 1 minus 1, where h is the height of the tree. Okay. For example, let me go back to the previous case, right? Now, what is the height of this tree? Can anyone tell me? This one, complete binary tree. What is the height where all the elements are filled? Yes, Atul. Can anyone tell me what is the height of this tree? So that we can compute what is the size requirement. Yes, Atul, you want to say anything? What is the height? First, just go and count number of edges from root to the leaf of this particular tree. So this is first, right? First, second, and third. Yes? Okay. Now suppose, and let's try to count how many nodes are there first of all. Yes? 1, 2, 3, right? Then, yes, number of nodes are 4 plus 4, 8, 12, then 14, and 1 is 15. Sorry, 15, right? So the total 15 nodes are there. So obviously we need to make a space for these 15 nodes. Okay. So what is the height over here? 4 or 3? Yes, 3. Okay. So let's calculate 2 raised to 3. What is that? 2 raised to 3 is okay, 8. Very good. Now, what we actually need to do is 2 raised to h plus 1, right? If height is 3, so 2 raised to 3 plus 1, that is 4. Yes, 2 raised to 4. Now, if 2 raised to 3 is 8, so 2 raised to 4 will be 16. Yes. Now, 2 raised to 16 minus 1 is what? 15. Yes. Now, just go and count all those nodes. So, this tree can accommodate, if a tree is having height h, so it can accommodate at most 2 raised to h plus 1 minus 1 nodes. Very good. Okay. Right. So here we need to take care or we need to represent that. Let me go to the next slide. Yes. So here we need to take care of this static representation, that is with the help of array, where we have, if there are n nodes, so sorry, if the representation is having height h, so we need to have an array of size 2 raised to h plus 1 minus 1 size or dimension. Okay, that can be your MCQ type of question during the examination. Okay, but in a link representation, as linked list is the flexible and dynamic data structure, yes, we go and allocate the amount of space whenever we require, right? But in an array case, we need to statically declare it before the utilization. That's why we should know how much amount of information will be stored with the help of that particular array, right? So in that case, we require the height of the tree. So in a linked representation, we will declare one structure and that contains a data and two links, or you can say two pointers. They are pointing to the left children and right children. Okay. So linked representation obviously will be efficient than the sequential representation. So we will implement our tree with the help of linked list data structure. Okay. Now let's say this tree is there with the same height, isn't it? Right? But it is not a complete binary tree. Now with this example, we can say that why we have to avoid using array for representing the hierarchical data. Yes, see how many nodes are there from this example. A, B, C, 1, 2, 3, 4, 5, 6, 7 and 8. There are only 8 data that we have to store. Yes, there are only 8 information or 8 data we have to store, right? But the tree height is 3. So how much amount of space we required? How much amount of space we required? We required the array of size 15, right? So let's say this is an array of size 15 at bottom. Okay. So let's say these are your indices. These are nothing but the indices I. And these are your values V. These are the values. Okay. Now, when we have to store this kind of tree into the array, what we need to do, we have to number them. Root will be kept at the 0th position. So we will number it 0. Then subsequent levels, we are going to number from top to bottom and then left to right. So let's say this is 1 and this is 2. Then this is 3 and this is 4. Right? Now you can see C does not have any left children, but as a static data structure, let's say I have added one dummy node and I am going to number it 5. Then this will be the 6. So moving further for the next level, yes. So again, there is no children to my node D. So I am going to add some dummy nodes over here. Yes. And number them like 7 and 8. Next numbers I am providing. Okay. Then this will be 9. Yes. Then this is 10. Yes. Further, there are no nodes at this level. So again, we go and add the dummy nodes, right? Over here also, let's add some dummy nodes and we can number them like 11. This is 12. Then 13. And last one will be 14 to make it as a complete binary. Because in a previous slide, we have seen for the complete binary tree, we required 15 array, 15 size, array of size 15. Okay, because the height was 3. Now suppose in this scenario, if one more node is increased, right? let's say we have added 1 children to H. Let's say that children is I. Now, what will be the size of this particular tree? Size will be 4. Yes. So, how much amount of space we will required? 2 raised to 5 minus 1. Right? 2 raised to 5 minus 1. But how many elements we are storing? We are storing or we are utilizing only, yes, 9 places or 9 elements. Okay. So, or within this example, you can clearly see that we have allocated 15 elements, right? But we are only using 8 elements. Okay. 8 elements. Rest of the elements like this one, okay. Okay, all those are wasted. There is a wastage of memory. If we represent the hierarchical data structure with the help of static array, or you can say static memory allocation. Therefore, we will better go for linked list. Okay. So let me check the time. Okay. So I hope you people are getting the concept of a tree, right? So we will continue tree in a next session. If you have any doubt related to the queue that we have just discussed in our first half of a session, and related to the topics that we have just seen from the queue, from the tree. Yes, till now you can ask me the questions because you people might have the next lecture as well.
Yes, sir.
Okay, sir.
Others, if you have any doubt, please use chat box to write your doubt, or you can directly unmute yourself. Otherwise, we will.
Yes, today I can see there are many responses in the chat box. People
Right.
are now
It's good.
putting some message and interacting. Yes.
Yeah, it's good as well because we want learner to interact with the faculty.
Yeah.
That is very good part of a session because we are here to clear your doubt and expect
Yeah.
more questions from you. So learners, I think today you don't have any question in this session, but still, if you have any question, please note down your questions and you can ask the questions into a next session as well. So,
Okay. So someone has asked one question over here. Yes. Karthik, yes. Can you give the priority queue example in a resource management, right? Or in a scheduling? I can give you one example related to the process execution. You see, suppose over here, now you can see there are some different tasks are executing, right? And some tasks are already executing in the background on my computer. Like right now, you can see one PowerPoint presentation right now, right? So let's say the PowerPoint presentation is the main process or main task which is executing over here. And suppose before start of this particular lecture, suppose I was trying to install something and it was taking some time. Let's say I was updating my antivirus. Okay, so it was executing in a background. Okay, so that is also a process, updation of our antivirus, and the PowerPoint presentation, which is going on right now over here, is also one of the process which is executing on my system. Yes, so as my PowerPoint requires the entire screen, so it is shown on my screen. So it has highest priority right now, right? But the installation is completing or it is updating in the background. Okay, but it is related to the system. It is related to the operating system's program. Okay, now once it is completed, now most of the time we can see one message box at this bottom or at the center of the screen. We can see meanwhile within our application, which interrupts the thing, interrupts our flow or which interrupts the display currently that you are looking at. Okay, so that shows my updation was initially in a background, but as it is completed, its priorities get increased. Now it is shown to the user. Okay, because from the system's point of view, that is the higher priority task, or you can say it's a higher priority process. Okay. Right now, higher priority process is PowerPoint presentation, but the installation is done at the system level. So it gets the higher priority ultimately, and it is interrupting. Or meanwhile, suppose I lost my signal over here, so there will be one pop-up at the bottom. Okay, so it interrupts the flow. So interrupts are having higher priority. Okay, that can be the example of you can say the priority queue. All the processes are kept in a queue, right? So the suddenly some process priority get increased and it is executed first. I hope I have cleared your doubt, Karthik.
Thank you so much, sir.
Thank you, sir. Thank you, everyone.
Yeah, and this is a wonderful session because it's a very important
उसको कर नहीं देना
topic.
था ना मेरे को जिसका नंबर उठाए पर वो
It's a very important topic too, sir. And
Yes, thank you.
the use of this topic is very in very much areas like AI and all. We use that this very
Yeah.
important topic to
Yes,
implement different applications as well. So thank you. Here we can end up the session, sir. And
yes,
thank you
sir.
so
Yes,
much
thank you
for
so
a
much.
wonderful session, Rahul.
Yes, I will share the PPT with you. Yes, thank you.
So thank you, learners, for joining as well. Thank you so much, sir.
Thank you.